Hi, I am Zhao from National Institute of Informatics. I will introduce our work on transferring neural speech waveform synthesizers to musical instrument sounds generation. Recent works show that musical sound synthesis can benefit from neural generative models. Related works have focused on either unconditional generation of continuous music or conditional synthesis of isolated musical notes. Meanwhile, approaches resembling the speech synthesis have been proposed for multi-instrument music generation, where a wavenet generates audio from the male spectrograms. A similar approach has also been proposed for singing sound generation. The similarities between musical and the speech modeling technologies suggest two questions. The first question is there a universal neural waveform synthesizer that is capable of synthesizing both speech and musical audio? The second question is, can musical audio synthesis benefit from speech models? This work tries to answer the two questions. Firstly, let's have a look at the three types of neural waveform synthesizers. The first type is neural autoregressive model. We call it AR model for short. AR model include WaveNet, SampleRN, WaveRN, FFTNet, ExciteNet, LPCNet, GloutNet, and so on. Parallel WaveNet, WaveGlow, ClariNet, and FlowWaveNet belong to inverse AR flow-based models. There are also some either AR non-inverse AR flow models such as multi-head CNN, GALP, HiNet, and neural source filter waveform models. AR models specify that the output waveform depends linearly on its own previous values and on a stochastic term. Inverse AR flow-based models are based on inverse AR flow framework, which is a general way of improving inference through autoregressive models. The third type doesn't use any AR or inverse AR strategy. For example, NSF is neither AR nor inverse AR flow model. It uses dilated convolution-based filter modulars to transform sine-based excitation into an output waveform, where the frequency of the excitation is determined by the input F0. For music signal generation, one potential advantage of NSF is that the F0 of the generated waveform is expected to be consistent with the input F0. This is due to the source filter structure of the NSF, where the sine source excitation carries the input F0, and the neural filter transforms the excitation into the output waveform without tampering with its pitch structure. In this work, we selected three representative neural waveform synthesizers: WaveNet, WaveGlow, and NSF. Each of them represents a kind of neural waveform modeling approach. Here is a configuration of three models used in our work. The backbone of WaveNet consists of a linear projection input layer that takes the feedback waveform as input. It contains 30 blocks of dilated convolution and a post-processing block that computes the categorical distribution for 10-bit quantized and mu-non-compacted waveform values. It contains 2.4 millimodal parameters in total. Both F0 and male spectrum are used as input to the network. WaveGlow model followed the standard configurations of NVIDIA's implementation. The third model is the harmonic plus noise NSF model with trainable maximal voice frequency. It contains a source modular, a neural filter modular, and a conditional modular. It has 1.2 millimodal parameters and its training speed is very fast. In this paper, we investigate transferring neural speech waveform synthesizers to musical instrument sounds generation on the three scenarios. The first scenario is training from scratch. It means generate the sounds with the model trained only on music data. The second scenario is zero-shot learning. It means generate the sounds from the model trained on speech data directly. And the other one is adaptation by fine-tuning. It requires both speech corpus for pre-training and musical instrument corpus for fine-tuning. This picture shows the two training stages required by a method named as adaptation by fine-tuning. The first stage is training speech model, and the second stage is to fine-tune the well-trained speech model with musical instrument corpus. We used VCTK corpus to train the speech model. We selected 87 speakers data from the corpus for training. The number of speech utterances was over 70,000, with a duration of around 21 hours. We used the URMP database as a musical instrument corpus. This corpus provides manually corrected F0 trajectories and the frame level about 10 ms. The database covers 30 instruments, including violin, clarinet, and trumpet. We used 149 tracks of recordings from the database for a total duration of around 4.5 hours. Each track has only one instrument. By following this figure, we can get 8 experimental models: WaveNet Scratch, WaveNet Zero Shot, WaveNet Fine-Tune, NSF Scratch, NSF Zero Shot, NSF Fine-Tune, WaveGlow Zero Shot, and WaveGlow Fine-Tune. We also used the nature sounds as reference. Thus, we had 9 experimental groups to evaluate in total. A perceptual evaluation was organized on a crowdsourcing platform to evaluate the quality of the generated waveforms and their similarity to the natural waveforms in terms of instrument timbre. This figure is the results in terms of the quality, and it is a abbreviation of natural sounds. Red dots represent the mean value of most score for each system. The result demonstrates the effectiveness of the fine-tuning approach for all three synthesizers. An interesting thing is that the system NSF-FT's quality score is not significantly different from that of natural samples. Also, WaveGlow showed great potential in zero-shot cross-domain adaptation. This is a result of perceptual similarity over each system. The similarity test has 5 different options, vary from totally different to absolutely the same. We use 5 colors to represent the ratio of the number of listeners for each option. The larger the gray and the yellow part occupies, the higher the sound similarity would be. We can see that the results of similarity evaluation is inconsistent to the quality scores case. More than 70% listeners thought the instrument timbre of the sounds generated by NSF-FT system are almost the same as the nature sound. This table shows the quality scores for each instrument of each system, respectively. There are 3 categories of instruments in musical corpus we used: strings, woodwinds, and brass. An interesting result is that, for some instruments, the most score of NSF-FT system is comparable to or even slightly better than natural sound. This is especially obvious for brass instruments. This is quite surprising. Now let's listen to some samples. If you would wish to listen to more samples, please visit our website. Lau comes to the conclusions. In this paper, we compared the performance of WaveNet, WaveGlow, and NSF on the synthesis of musical instrument sounds in 3 scenarios: training from scratch on music data, zero-shot learning from speech data, and fine-tuning on pre-trained speech models. The results suggest that pre-training even on speech data could help to improve the performance in terms of the music sound generation. Among the 3 synthesizers we examined, NSF performed best in both the fine-tuning and the training from scratch scenarios. Meanwhile, WaveGlow showed great potential in zero-shot cross-domain adaptation. For future work, we plan to evaluate the neural waveform synthesizers on other computers such as NC and MAE-STRO dataset. By doing so, we can test the models not only harmonic but also percussive sounds. We will also measure the impact of music data size on the training of neural waveform synthesizers. In addition, we plan to improve neural waveform synthesizers for polyphonic sounds with predict ML spectrogram from MIDI notes for end-to-end synthesis. Now let's use one more audio sample to end this presentation. This sample is mixed by 3 kinds of instrumental sounds, which were all generated by the common NSF-FT model. Thank you very much. Once again, please visit our website to see more samples.